Good morning, everyone. Thank you for coming. We are the surf transporter team. We are all senior mechanical engineering students. My name is Allie.
My name is Phil Baker.
I'm Haley.
Braden Hanson. My name is Luke Dagan.
I'm Tyson Boovie.
So to start off a little bit, I'd like to talk about our sponsors. So SURF, or the Sanford Underground Research Facility, is requesting this project to be completed. So they are a research facility based in Leeds, South Dakota. It's actually an underground mine that has been since converted into a laboratory. It's about 4,800 feet underground. Some of their goals are to advance world-class science and inspire learning across generations. Some of the research that they're doing includes neutrinos and dark matter and other things like that. So just a little overview of the facility. You can see this photo here on the right is a map of their underground location. And kind of up in this top upper left corner is kind of where we're going to be focused in our scope of the project. You can see the Yates shaft is that elevator that our cart will be taking. And then this 3/4 of a mile span down to this area by the number 4 winds is also in our scope of the project. And then up on this left picture is the above ground portion with the fill station and the Yates cage elevator.
So I'll take it away with what our project is actually encompassing at this facility. So kind of as Haley alluded to earlier, they have a lot of underground rail systems. It's an 18 gauge rail. And a lot of their processes and experiments use liquid nitrogen to run some of their equipment. And so those come in these very large tanks. They're called dewars. They weigh 600 pounds. They're about the size of a human, 64 inches tall, and they're 20 inches in diameter. So these are very big. And currently, they transport about one of these at a time through the 3/4 of mile up the 20-minute elevator ride when they have to refill the dewars and take them back down. So it's a very inefficient process. And it's a very time-consuming process as well. And so what they're asking us to do is to create a cart capable of transporting 6 of these at a time. They think that's an optimum number to make their process more efficient and to optimize this process. And this is going to be need to lift to a safe traveling height. So that's going to need to be mechanically operated, as we cannot use any sort of battery on this cart because of the environment. So I'll have Haley switch to the next slide and I'll kind of talk about some of the objectives of our cart and the process. And so what that's going to do is we're going to be able to move 6 at a time versus 1 at a time right now. And it's going to be mechanically operated lifting, so it will be less strenuous and safer on the operator using this transporter cart. And we're going to have to really focus on the accessibility of these carts, because in a lot of these tunnel systems and rail systems underground, there's not much accessibility. So for example, they might need to all be loaded onto the cart from one side versus being able to load from both sides. And another unique thing about this is they won't potentially be using 6 dewars at a time on this cart. We're going to need to be able to cover a variety of different arrays of loading. So anywhere from 1 to 6 dewars in any sort of orientation. And then also on there's some constraints we have to, some really tight constraints we have to focus on. The elevator takes a maximum load of 10,000 pounds. So if you do a little bit of quick math, you can see that 6 of these dewars is already 3,600 pounds that we have to lift with a cart. So this thing's going to be pretty heavy anyways. And then some of the dimensions that we have to worry about, the width and the length of 4 feet and then 12 feet long, that's the elevator layout right there. And then the height is actually not the elevator. That's the highest location or the lowest location throughout that traversal path that the cart will be taking. That 77 inches is like a doorway somewhere in the mine. So these are really, really tight constraints. When you take into account that just the diameter of 2 of these dewars next to each other is already 40 of that 48-inch width. And then if you go the other way, that's already 60 of those inches in length. And also I mentioned earlier that the height of those dewars is about 64 inches. And so looking at the 77 inches, that's really tough. Another thing about the environment down in the facility is there's several different types of environment that's going to be encountered in the process of transporting these dewars. So that fill station picture you can see, the above ground, that's one of the cleaner portions of the mine that this transporter will be experiencing. But then some of these tunnel sections are just an awful environment. They're going to be dirty. There's going to be rocks kicking up in the transport path. And also there's a lot of moisture in the air down there because there's a constant water flow through some of the wind shafts down there. And so this is a really hazardous and corrosive environment for anything that's going to be transported throughout. And then the last little bit I'll touch on quick before we jump into some of our designs. Kind of the cycle that this transport will take. So they're going to be loading empty dewars from down in that shaft. They're going to be driving this cart. It's going to be pulled via a locomotive that's already down there that they use. That's going to go about 3/4 of a mile to an elevator, 20-minute elevator ride back up to the surface. They're going to transport it over to the fill station. They're going to take it back to the elevator, back down, and they're going to be able to unload and then repeat this cycle. So you can already see that doing 6 at a time is way more efficient than 1 at a time. So I'll hand it off to Tyson for some of the state of the art.
As we started our project, we kind of wanted to do some research into maybe some possible things we could use as inspiration for our cart model. And a couple of the things from that state of the art were a lifting mechanism and a tank transportation technology, just kind of the current things they have around the world. So we've got kind of like a scissor lift, a forklift, a pallet jack, a Tommy gate, and a pulley overhead hoist. Just kind of has some rough ideas of what can we use for this project. And then tank transportation technology, maybe even implementing one of those lifting mechanisms or movement systems into our design as well, just for kind of, similarity. And then as we get into the next slide, it kind of shows what we're currently what Surf is currently using down in the mine. This is on the left is a Zimmerman cart. It's used for whatever they need. It depends on what they're storing for the length and the size, but generally it's very, very large. It'll be longer than what our current cart will be sitting at. And then on the right is just kind of a basic cart that is used down there for other things that they need to have stored around the mining area.
So this is the Westco dolly that they currently use at Surf. Just for a size reference, you can see it is about the size of a person. So not your typical cylinder, but this dolly that they use, we are planning to utilize in our design. And so it has a hook that will hook up into the top ring of that dewar, and then it'll be strapped around, and then a foot pump with hydraulics is utilized to lift that cylinder up off the ground.
So then, as Phil kind of alluded to earlier, we have some tight width and length constraints, which are driven by the Yates cage elevator, which is just the smallest width and length that we will be traveling through. So then over on the left-hand side, or on both of these, you can see the red on the outside is the constraints of the Yates cage height. And then the gray bar in the center back is the height constraint we were given by Surf themselves. So if you just put the cylinders themselves on the ground, we are left with about 13 inches to work with for our lifting mechanism. And then when you add a simple 8-inch wheel and 4-inch platform of our cart, we only have 1 inch to work with. So this kind of just represents our very tight constraints that we're working with. And then with an 18 gauge rail, which is just they're 18 inches apart, and then 20-inch diameter dewars, we were initially concerned with the stability of our cart because this leaves the center of gravity of our dewars lying outside of the reaction forces that the wheels provide. So if we just did under worst case assumptions, being that 3 full dewars are on one side, which is about 1,800 pounds, that dewars are flush with the edge of the cart at a maximum width of 48 inches, and we just take a static for a moment around point A, we just need the cart to weigh at least 1,000 pounds, and with our current design, it is at 2,500 pounds empty. So we checked this one off of our concerns.
So kind of hopping into one of our first decision matrices that we did, the pictures on the left there, the gray, as Ali said, represents our width constraint that Surf gave us, and the red is the Yates cage elevator that's also pictured there on the right. And as stated, these dewars need to be accessible and spatially optimized in order to fit in those constraints. So we looked at 4 different dewar orientations, row 6, 2 offset rows of 3, 2 rows of 3, and then kind of 2 pods of 3. And just looking at our some of our criteria that we took into consideration based off of Ali's statics calculations, centered weight was kind of weighted the lowest. Ease of access was very important to surf as they need to be accessed from either side. And spatial optimization was the highest because of those type constraints. And 2 rows of 3 ended up winning this decision matrix.
And then to kind of dive into some of our lifting mechanisms that we took into account, we had 4 main considerations. Our first being an overhead crane, and that would be something you might see in a shop for lifting very heavy objects. We had a drop deck trailer as our inspiration, an overhead gantry system that would be kind of an XY translation, as well as an engine hoist. And then if we dive into the decision matrix for those, we had many different criteria that we took into account, ultimately arriving at our drop deck mechanism as our most feasible process of lifting.
Yeah, so kind of getting into our dewar housing or our securement method for these dewars on our cart to make sure that there's no tipping or anything like that. We looked at a few different options, including typically seen straps and chains, a cage enclosure around all of the dewars, and then a buckle clamp, protrusions or recessed rings on our cart. And then moving into the matrix, we had 3 criteria, including secureness, ergonomics, and size, with secureness being our most heavily weighted option. And then after ranking all of these, the straps and chains did win. So we will be implementing straps onto our design as well as protruded rings on the cart to help with translational motion.
Now I'll kind of dive into the chassis material that we'll be using for our cart. While aluminum is a very good metal to be using because it's got a high strength, it does not weigh a lot. And we need this cart to weigh a lot, as we saw from our statics calculation earlier. So steel was our best option, and we have 5 different steels we kind of researched, with 2 common steels with the 36 and the 500, and then 3 HSLAs, which is high strength, low alloy. And as we get into our decision matrix, we have 5 different criteria: ultimate strength, cost, corrosion, availability, and weldability, with ultimate strength being the highest because it does need to hold that 3,600 pounds for a full cart of dewars. But cost will be coming in second, as we have, our budget. We have to stay within our budget. Availability and cost kind of go hand in hand, because some of those HSLAs, while their strength is quite high, they're not very available. They have long lead times, and they cost a lot of money. So based on those kind of criteria, the A36 won out as it's the most widely available. It's very cost efficient. The strength is still enough for what we need to use it for, and it's very easy to weld. We don't need any special tools or training for that.
So then another thing we have to consider about our chassis, you might remember earlier I was talking about the corrosive mining environment that this transporter will be used in. And so with that, we're going to need to make sure that there's no corrosion with any of our chassis on our cart. And so we're going to need to do some sort of coating on that metal. And so we looked at 3 pretty viable options: powder coating, painting and priming, and then also an epoxy coating. And so we'll dive into the decision matrix for that. And a few of the criteria we looked at were cost, durability, the adhesion to the steel that the coating would have, and then also the simplicity of the application of that coating, with the durability being the most important to us because it does need to have a good enough film to counteract any of the corrosive environment that it would encounter. And so you can see that the enamel paint and primer was pretty close to the epoxy, but this one won out mainly because of the application simplicity and the cost. So any of them are going to be about the same durability, but the fact that we can do in-house priming and painting of our chassis is going to save a lot of money and also time, like that lead time in the manufacturing and fabrication process.
Perfect. And then to kind of reiterate all of the decisions that we had made within our design, we are going to choose to use a 2x3 tank orientation paired with a drop deck that is hydraulically actuated. We're going to use straps as well as a ring protrusion to secure those dewars from translation, as well as using A36 steel and an enamel coat and primer. Perfect. So then kind of taking a look at what that might look like in an actual CAD model here, we have all of the previously indicated design decisions, as well as we have a rotating wheel carriage, a bifold ramp, and then you can see our hydraulics in there with our strapping mechanism. Perfect. And then kind of taking a look at what this would look like in the mine. So these are two areas in the SURF facility that our cart would actually encounter. So at the left, you can see one of the areas just outside the Yates cage, and that's where they store some of the current dewars, as well as at the right is an indication of one of our actual unloading zones. So if we jump to the next slide here, we see just kind of a basic representation of what our cart might look like in these actual locations under the mine. Perfect. So then this outlines kind of just a basic animation of our design with our bifold drop deck going to our hydraulics, our lifting carriages there. Rotating around, we see a human that is using the Westco dolly in conjunction with our design, going up that ramp to traverse the loading and unloading section, as well as an overview of our strapping mechanisms. So you can see at the top there, we have lifting brackets for further securement of our processes.
So kind of just touching on some of the first semester testing that we've been doing. There, as you can see, is a representation of those ramps. And we wanted to see if we were going to need to incorporate 2 or 3 feet on these. We originally wanted 2. After applying a load of about what a dewar and a person in the dolly would be there in the center, we found that the steel was actually yielding. So this kind of just shows how we modified our design into why we are incorporating a 3rd foot. And then here is a model of our wheel carriage, our pivoting wheel carriage. You can see there's a center in there, a center hole. And this just shows the factor of safety, and this only experiences about 4 KSI of stress and a factor safety of 9. And then this shows our original frame design paired with our new frame design. On our original frame design, I'll come up here and point this out. As you can see, our load path from our hydraulics will be traveling through there, and then it kind of stops. So we had a high stress concentration on these edge beams there. And in our new design, we incorporated these beams in our load path. Will travel more under the cart and distribute kind of that moment load throughout everything. And then the next slide shows our new model and what that looked like. So now our stress concentration is only about 13 KSI there at the center, and then minimum factor safety of around 3.
Kind of getting into some of the hydraulic sizing calculations we've been kind of doing. We wanted to make sure that whatever hydraulics we are picking, they're not going to buckle when they're lifting. So we want to make sure that works. And using our second moment of area, the ram modulus elasticity, our 5-to-1 safety factor, and the length of stroke, we found that our buckling force would be around 233,000 pounds, which is more than enough. It won't be anywhere close to that. So we know that our hydraulics won't be failing when we use them.
So another kind of hydraulic sizing calculation that we did is how much pressure will we need throughout the system to lift the amount of weight that will be applied on the top of the cylinder. So what that is it's a flow in equals flow out type of thing, and that flow out is converted all to the mechanical lifting that will be done within the cylinder used. And so once again, we found the reaction force the cylinder is going to be on. You can kind of see how the flow splits in our hydraulic circuit flow diagram. And so on the left of that diagram, it indicates a foot pump that will be mainly used, and then it kind of tees off and goes to 2 different cylinders, which represent the cylinders on either end of our transporter, right above those wheel carriages. And so basically, we just figured out that the flow that is going to need to be present with a 5-to-1 safety factor is about 3,800 PSI anywhere. So that indicates that our pump will need to be able to supply that amount of pressure throughout the entire system.
So then this is our Gantt chart. For those of you that don't know, it basically just paints a picture of what our year is going to look like with some of our presentations and due dates throughout. So as well as how long we estimate them to take us. So this is just our first semester up until right now, the Senior Design Conference. And then our next semester starting with the Critical Design Review in January all the way until our second expo, and then delivering the project to SURF themselves.
And kind of capping off the presentation with a rough overview of our budget, we were given $15,000 from SURF to complete this, 10,000 for materials, 5,000 for travel. And we can allot that however we see fit. We just decided to keep it at 10,000 and 5,000 for now until we get more information on some of our parts. Right now we have kind of 5 different criteria: our hydraulic system, our chassis, our manufacturing, our testing rental, and then our travel budget. Having all that there with rough estimates of what we need, we're at 15,000, but we're very confident that we can probably get this lower and not spend all of that. Some of these are, blank, like rails, welding, and form parts. Those are things rails we are receiving from SURF because it's hard to find rails places, and then welding and form parts we're going to do in-house here when we make our design. And we'd like to open the floor for any questions.
I have one question. Was the strap the popular vote, like is strapping these down?
So the question was, how did we come to the decision that we're going to be using a strap? And I have 2 answers for that. One, it's the most commonly used in industry, but also if you think about like redundancy in the design, right? We want this to be safe. We want there to be absolutely no slipping or any potential risk of anything for that in the safety regards. And so if you think about the dewars themselves, they're already 600 pounds. And so they have a lot of self-weight already.
Right.
And so if we have a slide here after this that kind of says like, so you'd be worried about going around a corner. We have a 29-foot radius as our maximum corner. And so we did a centripetal force calculation on this. And so the centripetal force that 600-pound dewar is going to experience is only about 48 pound force, whereas the friction force based off of a common coefficient of friction for A36 steel, about 0.8, you have 480 pounds of friction force already. And so that's already enough to overcome the centripetal force. So the strapping is just a redundant feature that's very common in industry that we're choosing to make it even more safe.
What about on like your linear deceleration? What rate is this thing decelerating and accelerating?
So if you go to the next slide, we also did kind of like a worst case scenario on what would happen. So the locomotive is going to be pulling this transporter at about 5 miles per hour would be the fastest it goes around that. And so we simply applied like the next slide. Yeah. A scenario where if it were to hit a wall, how much would that dewar displace at that maximum velocity? And so without any strapping or any protrusions or anything like that, it's only going to move about 7 inches, which obviously that's not great anyways, but the strapping is just very redundant and as well as the protrusions, redundant safety features. Yep.
So for that like dolly thing that comes with SURF, are you guys required to transport that with the trailer, or will that be at every location of the tanks?
Sure. So that's one thing we are still working on contacting SURF about, if that will be at just one location. And one thing we've thrown around is the idea of purchasing an additional Wesco dolly for the additional loading and unloading zone. And then one thing that it might not have been super clear is the loading unloading process. So a locomotive will pull our cart along the rail, the 18 gauge rail system, through those curves, hence our rotating wheel carriages. Our bifold ramp will fold down, and then that Wesco dolly will be used by the person unloading and unloading the dewars, and that will be at the location as necessary. And again, we're investigating, looking into having an additional dolly at those other locations.
The cart is raised by a foot pressure, right?
Yes.
How have you done calculations on how many pumps it takes to lift it?
Yeah, so the question was the actuation of our hydraulic system is foot pump actuation. So how many pumps would that take to actually raise and lower our full loaded cart?
Yeah, so I can kind of speak on that. So what the foot pump, so one thing we mentioned earlier, very briefly, is we can't have any sort of battery. And so that takes out any sort of air compressor operated pump that could be used. And so it does have to be all manual lifting. And so this is kind of goes off of that efficiency thing. Like we talked about how currently they do it about 6 individual times, and we want to only have to do it once. And so obviously you can take a look at kind of that with a 2-stage foot pump. There's kind of a wide range of strokes that could be needed to do. And it doesn't sound great to have to like pump this up about like 75 times at maximum. But if you think about it, we think it's going to be about 38 to 45 pumps. And if you think about how long that's going to take to do this, it's under a minute. And so that's already so much more efficient rather than having to do it 6 individual times. The numbers make it seem kind of a daunting task to have to, pump it. But in reality, that's like just as common as jacking up a car if you have to change a tire.
How does your cart interact with the locomotive? Is it pushed?
We will be incorporating, so they have hitch points on the carts that they have there already. So we're gonna be incorporating a hitch point on there at the designated height of the locomotive. And the Yates cage elevator goes through, so we need to have a hitch point on either side of the cart so that the locomotive can pick it from either side.
And is there one on the surface?
Actually, I don't know if there's one on the surface or not. They said we do not have to worry about that. They said they have a locomotive and they're not worried about moving it up there. So they must have something
heavy to.
Oh yeah, it's not getting pushed. They must have something up there too.
Okay.
Are the locomotives electric?
So the question was, are the locomotives that SURF uses electric? So that's something we actually haven't discussed with SURF. I think we believe that they could potentially be diesel powered, but that is something, as they do have like skid steers and other mechanisms that they use for devices underground. That answer your question?
And we asked SURF if they were concerned at all about these locomotives pulling the weight of this, and they didn't seem concerned at all since those Zimmerman carts, they carry so much weight. They said pulling this should not be a problem for their locomotives.
How hard is it for someone with one of those carts to actually load it on your cart? You're using one of those hand carry things?
Yeah, so one of the careful design considerations that we took into account was the actual angle of that ramp. So our overall deck is only about 2 inches high. So that angle is extremely minimal. And one thing we also made sure to take careful consideration into is the actual tipping of that dewar, taking into the safety of the user into account. So we had a maximum angle going down that ramp of approximately 6 to 7 degrees on our actual dolly. So that take minimal force and minimal risk for tipping of the dewar on the user themselves.
I don't know if you could tell by the video of the dolly, but the wheel diameters are 10 inches and 8 inches on that thing. And so if you think about that compared to the 2-inch flushed drop deck.
All right, thank you for the question.
Thanks for coming, guys.